All right. Welcome to lecture 38. This is chapter 9, section 3. We're going to be talking about gas stoichiometry. Now, you may remember stoichiometry. Hopefully you remember stoichiometry. It's one of those things that never, ever goes away in chemistry. That's when you have reactants going to make products. Oops. No. If I give you some number of moles of A, how much of C can you make? And so on. And you may remember that you have to be able to go from grams to moles via the molar mass, and then from moles of one to moles of the other using the stoichiometric factor. That's the the coefficients. And then so moles of A, grams of A, moles of C, and then back up to grams of C. So now we're going to be doing pretty much the same thing, only we're going to be looking at gases instead of solids and liquids and dissolved things. So it's more of the same, just now with gas laws tacked on top. It's just a well, it's the same thing. Nothing too new here, just putting together two things we already know. So first, we are going to start by talking, of all things, about density. Density, you may recall, is equal to mass over volume. This right here is the Greek letter rho. It's often used to represent density. For example, it's used to represent it in the textbook. So I'm going to go ahead and use it for this discussion of density. Now, molar mass, let's go ahead and just call that capital M, is equal to moles, grams per mole. There we go. I fixed it. Okay, so grams per mole. And then we have PV. PV equals nRT. So let's go ahead and see what we can do with all of this. Well, let's go ahead and bring this down. M equals rho V. So now let's go ahead and plug that in for M up here. Capital M equals rho V over N. But now let's go ahead and, for various reasons, we just go ahead and rearrange this to get N over V. It's going to be rho over M. Where remember capital M down here, that is the molar mass of our gas. Don't worry, this is going somewhere. Now let's go ahead and rearrange PV to get us N over V. It's going to be equal to P over RT. So P over RT is equal to rho over M. Wow, this is kind of strange. Why are we doing this? Because we can rearrange this part here to get capital M is equal to rho RT over P, or dRT over P, which is why I call this the dirt pile. Not for any particular reason, except that maybe that'll help you remember it. The molar mass of a gas at some temperature and pressure is going to be related to density, temperature, and pressure. In other words, this is how, once upon a time, they were able to measure the molar masses of things. It's because they were able to measure the density of a gas at a given temperature and pressure. So that is just a handy-dandy result. So there is a heck of a lot of algebra in there, rearranging variables and letters and so on. But this down here on the lower right is the point. Molar mass is equal to density times R, the universal gas constant, times temperature divided by pressure, the dirt pile. So let's say you measure the density of a gas as being 3.2 grams per liter at STP. Remember, STP is standard temperature and pressure, so 0 degrees Celsius and 1 atmosphere. What gas might this be? Well, molar mass is equal to dRT over P is equal to 3.2 grams per liter times 0.08206 liter atmospheres per mole Kelvin times 273 Kelvin. Remember, 0 degrees Celsius plus 273.15 gets you 273 Kelvin. I rounded. Divided by 1 atmosphere. So liters cancel, atmospheres cancel, Kelvin cancels, and it's going to leave you with grams per mole for your units. And when you do the math, you get 71.69 grams per mole. Obviously, we have some rounding errors there, but this looks an awful lot like chlorine. All right, that is just one example of the sort of problem that you might see with the dirt pile. Now let's talk about the law of partial pressures. Let's say you have a container that has 3 gases in it, gas A, gas B, and gas C. Gas A exerts a pressure of 2.50 atmospheres. Gas B is 0.500 atmospheres. And gas Z is 0.250 atmospheres. What is the total pressure inside the container? Turns out this is really, really simple, because the total pressure is equal to pressure A plus pressure B plus pressure C. It's equal to 1 atmosphere. Okay. So pressures are additive. Nice and simple. Okay. So the general rule, to write it all fancy-like, would look like this. That is to say, the total pressure is just the sum of all the pressures. You add all the pressures together, and it'll give you the total pressure inside your container. P1 plus D2 plus P3 plus dot, dot, dot. And so on. Okay, you just add up all the pressures that gets you the total pressure inside the container. Which brings us to another useful tool, because there's always more useful tools, right? In this case, mole fraction. It is directly related to pressure, okay, and partial pressure. So if gas A is just one of several gases, B, A, B, C, and so on, then the partial pressure of A is just the pressure exerted by A. Okay? But Pevnert applies like so. Because the gases are all in the same container, they all have the same volume and temperature, but they have different numbers of moles and different pressures, right? So PA times V equals NA times RT. PB times V equals NB times RT. Each of the gases inside that container is going to have its own Pevnert equation. So PA is equal to NART over V. PB is equal to NBRT over V, and so on. So the total pressure inside of our system is just, so NA plus NB plus NC plus, and so on, times RT over V. Because NA times RT over V is just PA, PB, PC, and so on. So this is another way of writing out the law of partial pressures, just FYI. You don't have to calculate each individual pressure. You can just get the moles of each and then calculate the total pressure from the total number of moles. But there's more. Because PA over the total pressure is equal to NA RT over V divided by NA plus NB plus NC RT over V. Cancel out the RT over V, because that's the same thing. You get NA over NA plus NB plus NC, and so on, or mole fraction. Now remember, mole fraction is just like mass percent, only we leave it in a fraction form instead of turning it into a percentage. That's all. So what you can do is you can say that the partial pressure of A is equal to the total pressure times the mole fraction. A lot of times it's important to keep partial pressures in mind, even though you can't directly measure the partial pressure of any individual gas. You can easily measure the total pressure of all the gases inside of a system, but you can't separate out the individual pressures. But if you can keep track of the number of moles of everything floating around in there, if you can keep track of your mole fractions, then you'll be able to get partial pressures out of that. Okay? So knowing the mole fraction of each of your substances and the total pressure will get you the partial pressure of each of those substances, which can play a role if, for example, you have, say, oxygen and argon flying around somewhere. You often keep things under, say, an argon or a neon atmosphere in order to prevent extraneous reactions, so that you can keep things under better control. And by measuring the change in pressure inside of a system that already has a gas, you're measuring the buildup of your new gas. Okay? So that's one of the things that comes out of our law of partial pressures, is the relationship between the partial pressures and the moles, and then from moles and mole fraction, until finally you get this equation down here. The pressure exerted by each substance within a mixture of gases is equal to the total pressure of all the gases multiplied by the mole fraction. And that should probably be A right there. So let's talk about a useful sort of practical tool. Collecting over water. If you're producing a gas as one of your products and you want to collect just that gas, you don't necessarily care for the moment about your other products, it can be difficult to, keep a gas from escaping. It's also difficult to create a reaction chamber that can change in volume along with your gas, or that is capable of withstanding a wide range of pressures, as you go from no gas to some or maybe a lot of gas. Fortunately, there's an easy solution, and collecting something over water is it. Okay. So you have, your big reaction vessel. And your reaction feeds, gas in a tube like this into a water bath. This upside down container here starts out completely full of water. Think about a manometer, only it's low enough that it's just completely full of water. And then this bubbles gas up into here. And then, the water level, slowly decreases as you get more and more gas filling inside of that container. So that is a way to isolate a gas that you don't just want escaping into the general environment. Or, it could be that you want to collect it specifically because that's the product you're interested in. Or it could be that it's, highly toxic and you're not an evil person. You want to keep it from poisoning people. So collecting something over water is a good way to do that. Now, if you're interested in maintaining, a nice pure product, you have a problem. Because the total pressure inside that container is going to be the pressure of your product, whatever it is, plus the pressure of water. Because all liquids have what's known as a vapor pressure. Okay, so it's called PVAP, usually. It's just that there's always going to be some amount of the liquid entering the gas phase. Okay, all liquids evaporate, some fast, some slow. Some very, very slow. So there's always going to be some vapor pressure there. So what you want to do is you want to take into account the amount of water, if you're collecting over water, that is going to be mixed in with your gas. So what you would do is you would look it up on a table, that has, say temperature and the vapor pressure of water at that temperature, 0, 5, 10, 20 degrees Celsius, and so on. And then you would just say, okay, so Px is going to be equal to the total pressure minus the vapor pressure of water. And that's how you can know how much product you've made, because Px is equal to Nx RT over V. So that's just another example of how partial pressures play out in reality. Now, let's finally look a little bit at stoichiometry. At constant pressure, volume of your system is going to be directly related to moles, because these three things over here are going to be constant. Similarly, at constant volume, pressure is only dependent on moles, because these three are constant. So when doing a stoichiometry problem, AA plus BB goes to CC plus DD. Instead of going from grams to moles to grams, you can now substitute volume and pressure in for grams or moles. Okay? Now, all roads still lead to moles. Everything goes through moles. But when sometimes you can, sort of make a shortcut. And that's what gas phase problems allow us to do. For example, when you mix hydrogen and oxygen to make water, it's always going to be 2 moles of hydrogen plus 2 moles plus 1 mole of oxygen will always make 2 moles of water. But at a given temperature and pressure, you can also say 2 liters of hydrogen plus 1 liter of oxygen will make 2 liters of water. gaseous water, by the way, because volume is only related to moles. Okay? Or at constant pressure, at constant volume, you could say 2 atmospheres of hydrogen plus 1 atmosphere of oxygen, will yield 2 atmospheres of gaseous water. So that is what we're getting out of stoichiometry here. You can sort of substitute volumes or pressures in for moles under the right conditions. Because at constant pressure, volume is directly proportional to moles. At constant volume, pressure is proportional to moles. So you still have to be careful, and you still have to go through moles, sort of. But it's just an advancement, a continuation of the sort of work we've already done. So you can expect to still solve any sort of stoichiometry problem, only now you're going to be using gases and pressures and volumes instead of necessarily just masses and moles. And you can still, be expected, say how much reactant does it take to make a certain amount of product. You can still do percent yield problems or limiting reagent problems, anything like that, using gases, pressures, and volumes. All right, and that will do it for section 9.3. I'll see you in the next video for 9.4.